Hello, chemists. This is Ms. Blagino, and you're watching lesson 7.7, Gases and the Laboratory. Today we're going to talk about how to work with gases experimentally. If you're considering taking the SAT-2 in chemistry, this is a topic that comes up that is a little bit beyond the scope of the regular Regents curriculum. So I want to take some time today to talk about it, and it's also just kind of practical information as we will be working with gases in the lab. Some goals for today's lesson. You should be able to take measurements using a manometer. That's not pronounced a manometer, it's a manometer. You should be able to describe proper techniques for the collection of different gases. This is a big one. And you should be able to determine the partial pressure of a gas collected over water. We will be doing this in the lab, but this is a question that shows up all the time on the SAT in chemistry. All right, let's get started. So I want to look at measuring the pressure of a gas. You may have seen a barometer before. Barometers are pretty easy to read. They're kind of analogous almost to like a thermometer. So I want to look at manometers, which are slightly different. There's a little bit more to it. So a manometer is something that looks like this, where you have a gas and this bulb, kind of this like U-tube, and it's open on one end to atmospheric pressure. And often you have something like mercury in there so that you don't have like massive manometers that you have to work with. These can be pretty reasonable sized. So this is an instrument used to measure gas pressures. It measures the height of a mercury column. That's this stuff in here. One end is open, atmospheric, and the other one contains a bulb of gas. So that is our general setup for the manometer. Here we've got three different examples, three different measurements that the manometer can have. We can end up with there being no difference in the height of the column. The height on the atmospheric pressure side is greater than that on the pressure with the gas. And the opposite, the atmospheric pressure, kind of the mercury level being lower than the side with the gas. Let's start off with this one first. If you end up with equal heights of mercury on either side of that U-tube, what do you think that might mean about the pressure of the gas and the pressure of the atmosphere? Hopefully you're thinking they're the same. Yeah, the pressure of the gas is equal to the atmospheric pressure. Neither side is kind of pushing down more than the other. What about this next situation? I'll call that one number 2. Which one has a greater pressure, the gas or the atmosphere? Let's see, it looks like the gas is pushing down this mercury column so much so that it's like lower on the side with the gas than it is on the side with the atmospheric pressure. So this must mean that the gas and the bulb has a greater pressure than atmospheric pressure. And finally, in example number 3, the opposite must hold true. Here the atmospheric pressure is pushing down greater than the pressure of the gas is pushing back. So we end up with atmospheric pressure being greater than the pressure of the gas. So when I go to calculate pressures, obviously really nothing I have to worry about for when they're equal. But I can use the heights as part of my calculation. So the pressure of the gas, in this case, case number 2, would be equal to the atmospheric pressure plus whatever that height difference is, because the atmosphere has less pressure than the gas, or alternatively put, the pressure of the gas is greater than that of the atmosphere. Opposite scenario for number 3. The pressure of the gas is equal to the atmospheric pressure minus the height of the mercury. In this case, remember, atmospheric pressure is greater, so we'll subtract the height to get the pressure of the gas. Before we get into anything new, let's try out a practice problem. Let's look at this first practice problem. We know the atmospheric pressure is equal to 748 millimeters of mercury. We've got a sample of neon gas, and the height difference is 5 centimeters between our sample and the atmospheric pressure. Before we just start to plug and chug, you need to be careful with the units. Units are always important, and it's no exception with manometers. My pressure is being measured in millimeters of mercury, and I've got centimeters of mercury. So to get from centimeters into millimeters, a centimeter is equal to 10 millimeters. So there's a 50 millimeter difference between the two heights of the mercury column on either side. In this case, which has greater pressure, atmosphere or our sample of neon? Atmosphere is pressing down more, it's pressing up more, so our pressure of neon, oops, I don't look very nice, is going to be equal to the pressure of the atmosphere minus the height of the column. So pressure of neon is equal to atmospheric pressure, 748 millimeters of mercury. Subtract the height, 50 millimeters of mercury. And the pressure of the neon gas should be 698 mmHg. The other two questions are very, very similar in nature, but even more conversions to contend with. So pay careful attention to units before you just start plugging and chugging numbers. All right, let's get back to the notes. Let's talk about how to produce and collect a gas in the lab. All right, so in this setup, we've got our test tube with reactants. We got like some solid, most likely, in the test tube. We're going to heat it up, decompose it, and then we're going to collect, in this case, ammonia, which is NH3, in the test tube. Now, at first glance, this might look insane. How on earth are you going to keep ammonia in that test tube? It's upside down. Isn't the ammonia just going to fall out of the test tube? Careful. The reason this is a smart setup is because the gas we're collecting is less dense than air. We know that ammonia has a molar mass of about 17 grams per mole, and air is nitrogen and oxygen gas at 28 grams per mole and 32 grams per mole, respectively. Now, I know that molar mass and density aren't the same thing, but since the numerators are going to be different, but the denominators will be the same, 22.4, for all three of these samples, I don't have to do any more math than this than to know that ammonia is going to be less dense than air. So ammonia gas tends to float, and it's going to get trapped up at the top of the test tube. And of course, I can't like make the executive decision, oh wait, we can get out if we just go down. No, it's less dense, so it will float. So we're saying thermal decomposition reaction to generate gas. Yeah, so we're probably going to use some ammonia-based compound here, or ammonium, I should say, decompose it, and collect our ammonia gas that way. But this is the type of setup you want to use anytime the gas is less dense than air. It will float up to the top of the test tube. You can, put a stopper in it when you're done. You don't have to worry about losing any ammonia. This is another gas collection setup. Okay, we use what we learned in the last slide. What do you think might be true about one of the properties of this gas? So we got a reaction taking place here, usually like an acid reacting with metal. We'll produce our gas, and it's going to get collected in this collection jar. Let's see, it's open at the top. This definitely wouldn't work for ammonia, something that is less dense than air. So this must be the setup for a gas that is more dense than air. Yeah. If we're collecting something like carbon dioxide, for example, CO2 at 44 grams per mole. Yeah, it doesn't really fit. But that's going to have a greater density than oxygen or nitrogen. So as we produce our CO2 gas, it's going to collect at the bottom of this jar. We don't have to worry about it finding a way to escape out. In this setup, we've got this thing called a thistle tube. Basically, this is how you're going to deliver your acid into the reaction. Got some metal at the bottom. One question that you'll see sometimes on the SAT is they'll talk about, they'll give you a setup and they'll ask what's wrong with this. And from time to time, it's the thistle tube isn't low enough. You need the thistle tube to be underneath the liquid level, because as you're producing the gas, if the thistle tube cuts off there, then some of the gas is going to escape back through the thistle tube. Some of it will be collected in the jar where it's supposed to go, but this is not a good use of your materials. So you always want to make sure that the liquid level of the thistle tube, the thistle tube is below the liquid level in your reaction vessel. Okay, we've actually used this technique to collect gases before, and we'll be doing it again in lab. What we have here is another thermal decomposition. We're taking potassium chlorate, heating it up, we're producing O2 bubbles, and we're collecting it via water displacement. So we filled up this container with water. This is a really good way to get like a nice pure sample of a gas. And as the oxygen gas is produced, it'll rise up to the top, and the pressure will force the water out of this container. This is only an appropriate method to use if you have a nonpolar gas being produced. Polar substances like ammonia would dissolve in water. So instead of the ammonia gas collecting up at the top, it would dissolve and create like a solution of ammonia instead of just ammonia gas. So something like oxygen, this works really well with. Carbon dioxide, also nonpolar. Hydrogen, nonpolar. This is a great technique to use. Not so great with your polar gases. So kind of building on that idea of collecting a gas over water, we have something a little bit more quantitative. This is pretty similar to what we're going to end up doing in the lab. We are collecting a gas over water, and we're going to determine the partial pressure of that gas in the tube. So just a little bit more information. This is probably going to end up being the reaction between some metal and some acid, and that'll produce H2 gas. Hydrogen gas, when it's collected over water, or anything that's collected over water, in this like airspace, we're going to have the H2 gas that we meant to produce and some water vapor that is in there as well. Our job is going to be able to determine what the partial pressure is of the hydrogen gas. Okay, so the first thing we want to do is convert this difference in height between the liquid level in the beaker and the liquid level in this tube to millimeters of mercury. So I've measured it to 93.17 millimeters of water. I need to get into mmHg. That's going to allow me to like kind of talk about pressure. So the conversion is for every 1 millimeter of mercury, it's about 13.6-ish millimeters of water. So in this case, I can just set up this conversion. Millimeters of water will cancel out. I'll be left with millimeters of mercury. So I get 6.851 millimeters of mercury. So that is the height difference between the liquid level in the beaker and the liquid level, in both cases water, inside this gas collection tube. Now that we've got the difference in height in terms of millimeters of mercury, we can move forward. Let's see if we can figure out if the pressure of the gas, so the pressure inside the tube, is greater than, less than, or equal to the atmospheric pressure. Well, this is kind of like the manometer problems that we were looking at earlier in this lesson. We know that we've got the gas in the tube pushing down, and then atmospheric pressure pushing down. So which one seems to have a greater pressure, greater force almost? It's the atmospheric pressure. It's definitely greater because it's kind of pushed this liquid, kind of think about it, up into this tube. And you know, the was equal, the height of the water inside the tube and inside the beaker would be the same. Atmospheric pressure is greater than the pressure of the gas. So let's find the pressure of the hydrogen gas inside the tube. We know that the pressure of the gas is equal to the atmospheric pressure minus the height, minus the partial pressure of water. Again, we've got that mixture of two gases inside the gas collection tube. We know the atmospheric pressure is provided. We figured out the height, it's like that 6.831 millimeters of mercury. And we know the partial pressure of water. So the math here isn't particularly complicated, but sometimes the reasoning behind it can be challenging. Well, I should say 3. So we can go ahead, those are all in millimeters of mercury, so I can just perform the calculation. Looks like I can have 2 places after the decimal point as far as sig figs are concerned. So I'm getting a partial pressure of 736.39 millimeters of mercury. That's about as complicated as I've seen the SAT to make it. Have you deal with differences in height between liquid levels, figuring out which pressure is greater, and then tying it into atmospheric pressure and partial pressure of the water vapor. I know this is kind of maybe a little difficult to visualize and work with. We will be running an experiment really similar to this in lab, and hopefully kind of working with it hands-on makes it a little bit easier to make sense of the calculations. As always, work on those practice problems that are included in this lesson. It will get easier. You'll get better at it the more you do. Okay, chemists, thanks for tuning in, and I hope you found this helpful.